All right, we're going to take a look at a process called completing the square, and this will help us solve quadratic equations. Is one of the things it'll do for us. That's the most immediate thing that it's going to do for us. So earlier, we looked at polynomials, how to find their degree, how to add polynomials, multiply, how to divide polynomials. And what's going to happen now is we're going to take a closer look at a specific type of polynomial. So um, one of the first things we learned about polynomials is that a polynomial has a degree. So for example, 3x plus 2 is degree 1 because the highest exponent on any of the variables is 1. So 3x we said was a monomial with degree 1, and 2 was a monomial with degree 0. And the degree of a polynomial is the same as the highest degreed monomial that it contains. So since x to the first, degree 1, that's our biggest degreed monomial, that's going to be the degree of the polynomial. So 6x squared minus 4x plus 5. The 5 has degree 0, the 4x or negative 4x has degree 1, and the 6x squared has degree 2. So this is a degree 2 polynomial because that's the biggest degree for one of its terms. And then just as another example, 4x cubed minus 2x squared plus 11x plus 1. This is a degree 3 polynomial because that's the biggest degree of any of its terms. All right, so what we're going to start to look at now is we're going to go more into depth with degree 2 polynomials, usually just with one variable. So not always going to be x, but that's a common one. So we're going to take a closer look at polynomials that take the form ax squared plus bx plus c. And x is the variable, a, b, and c are going to be constants, and they're just going to be real numbers. These are called quadratic polynomials, and they're degree 2. Okay, so we're going to take a closer look at what are called quadratic polynomials. All right, so the first thing we're going to learn, other than, because we already know how to find their degree and how to add them and multiply them, because they are just polynomials, the first thing we're going to learn that's kind of specific to quadratics is a process called completing the square. And the first thing we're going to use it for is to solve quadratic equations, but it's also useful when you want to graph quadratic functions, which we will do. And later this year, when we study conic sections, we're going to use this again when working with conic sections. So that'll come later. But for now, we're going to use this completing the square to solve quadratic equations and then eventually graph quadratic functions. Okay, so what do we mean by complete the square? So to complete the square, that's when you hear that, what we're saying is we're going to change a quadratic that's in this form, which is ax squared plus bx plus c. Again, a, b, and c are just constants. The variable is x. So we'll actually have numbers for a, b, and c when we do specific ones. We're going to change the quadratic from looking like this. We're going to do something called completing the square to make it look like this. So instead of ax squared plus bx plus c, where we just have each term being added or subtracted to the other one, we're going to make it look like this, where this a is this a, and then it's times the quantity x plus some other number p, that quantity raised to the second power plus some other constant q. So a, p, and q are constants and the variable's x. So we're going to take quadratics that look like this and we're going to change them to look like this. Now they'll be the same quadratic, it'll look different. And the reason we'll want to do this again is it helps us solve equations and it helps us graph and do some things with conics later on. And it's useful throughout mathematics, but I'm just giving you the specific things for this year. So here's the basic idea. Now keep in mind, don't panic as you read through this and write it down. These are the steps, but these are the steps for just a generic quadratic. So ax squared plus bx plus c, where a, b, and c could be any real numbers that you can think of. Most of the time, if not all of the time, we'll actually have specific numbers for a, b, and c, as you'll see in our examples. So step one is to make sure your quadratic is written in this form, where the second degreed term is first. If there is a first degreed term, it comes second, and then the constant comes last. Once it looks like that, you want to factor whatever this leading coefficient is, whatever a is. You want to factor this number. You want to factor that number out of the first two terms. Just the first two. Notice we just leave c alone. So we're just going to factor a out of the first two terms. Well, when you do that, you're going to get some other number in front of x now. So whatever's in front of x, we're going to take that number and we're going to divide it by 2, and then we're going to square it. So whatever number is in front of x, we're going to divide that number by 2, and then we're going to square that number. Well, whatever you get, we're going to take that number and we're going to add it to this term right here, the b over a times x. We're going to add that number to that term. But that's not really legal. You can't just add some number to an expression because you feel like it. So to make it legal, to make sure that we're working with the same quadratic all the way throughout, even though we added this number, we're going to immediately subtract off the same amount from the end of the quadratic. So we're going to subtract off this amount from c, and what that does for us is it keeps the quadratic equivalent to the original. So when we add this number to the b over a x, we need to subtract this number from the whole expression so that we keep everything equivalent. And then what that's going to do is it's going to leave us with a set of parentheses, and inside there is going to be a perfect square trinomial. So inside the parentheses is going to be something we can factor. Now this definitely looks scarier than it is, so let's give it a try and see that it's not too bad. So for this first example, we've got x squared minus 6x minus 3. And our directions are to complete the square. So right now it's written exactly as we want it. We have the x squared term first, and then the x to the first term comes second, and then the constant is last. Keep in mind, this does not factor. So there are no factors of 3 that add or subtract to 6. So this doesn't factor. It's what we call prime, as we learned back when we did all our factoring. This would be a prime polynomial. Prime over the integers, by the way, if we only use integers. So we want to complete the square. We want to change the way this looks to that other form, we'll see here in a second, but we want to change the way this looks by completing the square. All right, so first and foremost, we need to recognize that there's no number sitting out in front of x. And anytime we see that, we should remember that there really is a number out there. It's just positive 1. So that's our a. So the positive 1 right here, that's our a. The negative 6, that's b. And the negative 3, that's our c. So a is positive 1, negative 6 is b, and negative 3 is c. All right, so we're just going to follow our steps. The first thing we want to do is we want to factor a out from the first two terms. So this will equal, if we take 1, if we factor that out of the first two terms, 1 times what is x squared? Well, 1 times x squared is x squared. And 1 times what is negative 6x? And it'd be negative 6x. And then the negative 3, we don't touch it. Now, you might be thinking to yourself, why did we just do that? Because it didn't change anything. And you're right. If a is positive 1, then factoring it out, doing that first step doesn't really do anything. So you can actually skip that first step if a is positive 1. And a is not always positive 1, so we'll do one where it's not. All right, so next we want to take this number and we want to divide it by 2 and we want to square it. So we want to take negative 6, divide it by 2, and then square it. So negative 6 divided by 2 is negative 3, squared is 9. So we end up with 1 times x squared minus 6x, and then this 9 gets added right here, right next to that negative 6. And then here's our minus 3. Let me color code this, make it a little bit easier. 9. Our 9's right here. Now, I'm not allowed to add 9 because I feel like it. So to balance it out, I have to subtract 9 from the end of the entire expression to keep everything equivalent. So you can check. What we just wrote down should be the exact same thing as what we started with. So look, 1 times anything is itself. So we have x squared minus 6x plus 9. And then minus 3 minus 9. Well, let's collect like terms. 9 minus 9 is 0, so we end up with x squared minus 6x minus 3, which is exactly what we started with. So what I've done hasn't changed the quadratic, it just looks a little different. But by doing what we just did, by adding the 9 and immediately subtracting it, look what happens. I end up with x squared minus 6x plus 9, which factors into x minus 3 times x minus 3, which is x minus 3 squared, and then negative 3 minus 9 is negative 12. So we changed this quadratic into this quadratic. Now they're the exact same, they just look a little different. So this is what we want, and you'll see why we want this here pretty soon. But this is what we want when we complete the square. We want this quantity squared and then plus or minus a constant. So if you look back, all we really did was factor out a 1 from the first two terms. Then we looked at this number that's highlighted in yellow. We divided it by 2 and squared it. Gave me 9. I added 9 right after this term, and then I subtracted 9 from the very end. And I just factored what was in the parentheses, and then anything times itself is that squared, and then I just collected like terms. There's really not a lot to it, and after you do it a few times, you get the hang of it. So let's try a little bit more difficult one. So for this one, notice that our a is now a 2. So this will change things a little bit. So I need to factor a 2 out of the first two terms. So I just want to take a 2 away from the first two terms. The constant, I'm just going to leave it sitting there minding its own business. So if I take a 2 out, it leaves me with x squared plus x. Remember, I'm just factoring a 2 out from the first two terms. And then I want this number right here. I know you're saying, well, wait a minute, there's no number there. But yes, there is. It's plus 1. Don't forget, it's x squared plus 1x. So there is a number there. So I'm going to take that number, which was positive 1. I'm going to divide it by 2, and I'm going to square it. It's always this number right here divided by 2 and squared, which in this case, 1/2 squared gives me 1/4. So I always take what I get by dividing by 2 and squaring it. And I always right after this term. But I can't just add 1/4 because I want to. I have to make sure that this expression is exactly the same as the expression that came before it, or the one that we started with. They always have to be the same expression. So adding a fourth, I can't just add a fourth because I want to. So what I have to do is balance this thing out. Now, what makes it more difficult, what makes this one more difficult than the one we looked at before, is this a is 2 instead of positive 1. It's some other number besides positive 1. So what we can't forget is that there's a number sitting out in front of these parentheses. So what you've got to realize is that if I actually distribute the 2 back in, so 2 times 1/4, well, 2 times 1/4 is 1/2. So what I have to do is I added 1/4, and that's being multiplied by positive 2. So to balance this out, I have to subtract 2 times a fourth. Now, why do I subtract 2 times a fourth? Because what I actually did by putting the plus 1/4, it's really 2 times positive 1/4. So that's a plus 2 times 1/4. So to balance it out, I have to do a negative 2 times 1/4, or subtract that same amount. And if we did this correctly, I should be able to factor what's in parentheses right here. So let's give it a try. So x squared plus x plus 1/4. Well, that'd be x times x. And then to get 1/4, that would be 1/2 times 1/2. Let's see, to make everything positive, it needs to be plus for both of them. And then I'll have plus 5 minus 2 times a fourth is 1/2. Anything times itself is that squared. And then 5 minus a half, that would be, I need a common denominator. So that would be 10 halves minus 1/2. So I end up with 2 times x plus 1/2 squared. And then 10 halves minus 1/2, that's 9 halves. So here's what we get when we're done completing the square. So again, what we accomplished is we took this quadratic, we completed the square, and changed it into this quadratic. They're the exact same. That's what all these equal signs mean. So this quadratic equals all of these, but this down here is the form that we want. Again, why do we want that form? Well, for several reasons, but we'll talk about the first reason here pretty soon, because what we're going to do is solve equations using this process. So let's take a look at that. So completing the square can be used to solve any quadratic equation. Any quadratic equation. So that's important because what you're about to learn in this upcoming set of material is a bunch of different ways to solve quadratic equations. But not all the ways we're going to show you solve all quadratic equations. But this process will. So completing the square can be used to solve any quadratic equation. All right, so let's take a look at how to do that. So we've switched the directions on you. We now want to solve this equation, and we want to solve it by completing the square. So notice it's now an equation. X squared minus 6x equals 3. Well, the only way you knew how to solve this before was to move everything to one side and then factor. But if you look, this is the same quadratic that we did earlier. It was this one, x squared minus 6x minus 3. And remember, this quadratic didn't factor. So like it didn't factor. So the only way you've been shown how to solve this equation doesn't work. So we need something else. Well, completing the square is going to do it for us. Now, I picked this particular equation on purpose. We've already completed the square. We did it right here. Okay, so we don't need to go through all this step by step again, but the first thing we want to do is complete the square, and we see how to do that right here. So x squared minus 6x minus 3. We complete the square and get x minus 3 squared minus 12. So that's the same quadratic we have right here, x squared minus 6x minus 3. So the work will be the same. I'll go a little faster this time because we've already completed the square for this one. But we get x squared minus 6x. We divide that by 2 and square it, and that's where we got our 9. Then we subtracted 9. And then that factored into x minus 3 squared minus 12 equals 0. So this is what you would get after completing the square. And how does that help us solve it? Well, let's see how that helps us solve it. If I add 12 to the other side, I can square root both sides of the equation. Square root both sides of the equation. And when you take the square root of something squared, remember it's an even index, so the prisoner gets to come out of jail, but they're on probation, so it's x minus 3 absolute value equals the square root of 12. We can simplify that. That'd be the square root of 2 squared times 3. So we get the absolute value of x minus 3 equals 2 square root of 3. Remember, it's technically the absolute value of 2. So if we simplify, we end up with that. Well, I know it's been a long time, but earlier this year, we learned how to solve equations with absolute value on the variable. So we're going to need that here. And we learned way back in the day that when you take the absolute value of a variable equals a constant like this, when you solve this type of equation, we learned that what's inside the absolute value, which is x minus 3, it's either itself, which is x minus 3, or the opposite of itself. So this equation always split up into two equations. So if we add 3 to the other side, we get 2 square root of 3 plus 3. If we distribute the negative, subtract 3 from both sides, divide everything by negative 1, we get our two solutions that we were looking for. So we always write our answers as sets. So we were solving this equation, and the two answers are our solution set would be the set of all x, such that x equals 2 times the square root of 3 plus 3, or negative 2 square root of 3 plus 3. And we can check our answer just like we check any answer. We can take both of those numbers, plug them in for x, and see if we get a true statement, which I'll leave that up to you. We do. So let's try another one. So we need to solve this equation by completing the square. So there's our equal sign. So we have an equation. We move everything to one side. And notice we have 2x squared plus 2x plus 5, which is the same quadratic we did earlier. 2x squared plus 2x plus 5. So when you complete the square, you get 2 times x plus 1/2 squared plus 9/2. So I did that on purpose. That way save us a little bit of time. So earlier we did the work to complete the square. So I won't spend as much time going through that part right now, but we want to take out a 2. We divide We divide positive 1 by 2 and we square it, and that's where we got our 1/4. And then we subtracted 2 times that. And then that factored into x plus 1/2 quantity squared. And then we got the 9/2. And the reason that that helps us is look what we can do now. We can now subtract 9/2 from both sides. I can divide both sides by 2. And I can now square root both sides. So the square root of something squared we know is absolute value because our index is even. And then the square root of negative 9/4 we now know would be the square root of negative 1 times 9/4, which would be I, and then it'd be the square root of 9 over the square root of 4. Both of those are the principal square root, don't forget that. So we get absolute value of x plus 1/2, and then the principal square root of 9, the principal square root of 4, we end up with 3/2. And then we split this up into our two equations. So x plus 1/2 is 3/2 I, or negative x plus 1/2 equals 3/2 I. Subtract 1/2 from both sides. You can distribute the negative or divide both sides by negative 1. And then subtract the half. And we get our two solutions. We get 3/2 I minus 1/2 and negative 3/2 I minus 1/2. So we always write our answer as a set. So our solution set would be the set of all x such that x equals negative 1/2 plus 3/2 I not going to have enough room there to write that. So let's see, it will be the set of all x such that x equals, so we can fit it in down here, negative 1/2 plus 3/2 I, and then also negative 1/2 minus 3/2 I. That would be our solution set. So we have negative 1/2 plus 3/2 I and negative 1/2 minus 3/2 I. Our two solutions. And again, you can check by plugging these into the original equation and seeing that you come out with a true statement.